Let's move on to Physical Science, Module 11B, Force in Circular Motion. We'll be talking about the solar system, centripetal force, and centripetal acceleration. The weakest force. Remember that gravitational force is actually the weakest force. Gravitational force is so weak it can't overcome static friction. If the mass of an object is huge, as an example our Earth, the gravitational force can become considerable. So when you compare our Earth to our Moon, the force from the Earth is much stronger than that of the Moon. If a ball is dropped, Earth's gravitational force attracts the ball because Earth is so large in comparison with the ball. So even though the force is weak, the force still has an attraction from larger objects to smaller objects. Earth is applying a force on this ball. Newton's third law says that whenever a force is applied, an equal and opposite force must be applied as a reaction. So as the Earth applies a force on the ball applies an equal but opposite force on the Earth. As the ball falls towards the Earth actually rises towards the ball. And that's a hard concept to imagine, but it actually does. It's just that the force is so small coming from the ball that we don't actually think about the reaction to it. The acceleration of the Earth to the ball is very large because it's a large force. Because the ball is so small compared to the Earth, the acceleration of the ball to the Earth is not noticed. So there's actually an acceleration with this force. It's something we have to remember. And the larger the mass, the higher or faster the acceleration. Gravitational force acts to hold the planets and their moons in an orderly arrangement called the solar system. In experiment 11.1, the text demonstrated that circular motion requires a special force called centripetal force. In that experiment, we took a pen, pulled a string through it. We had weights on both ends, and what we did was twirl the lighter weight in a perpendicular motion to the pen. The force necessary to make an object move in a circle is what we call centripetal force. Centripetal force is directed perpendicular. So if you imagine this being a circle, this is the radius of the circle, and the radius is perpendicular to the center of the circle, to the velocity of the object, which means it points towards the center of the circle. So you can actually see it in this drawing. In the experiment, we had washers, and the washers were pulling on the string with a force equal to the force with which gravity was pulling on them. And without the centripetal force, or the motion of turning it in a circle, the washer, or like in this picture, a rubber stopper, would simply just spin off in a straight line. So if we took the string and cut it, the washer or the rubber stopper would just spin off. If this force, this centripetal force, is applied perpendicular to the velocity of the object will begin to curve. So think about the orbit of the planets. If the force continues to be directed perpendicular to the velocity of the object will move in a circle. When a force is applied, acceleration must occur. So I just mentioned that. But when we're talking about force, we're also talking about acceleration in this instance. Objects moving in a circle are constantly accelerating. Because the object's direction keeps changing, the velocity keeps changing as well. So the direction keeps changing as it moves around this circle. The acceleration is called centripetal acceleration. So from our text, they had a figure 11.3. And in the circular motion of this toy airplane that we can see, the airplane's velocity at any instant is directed straight ahead. So its velocity is straight ahead. If it wasn't attached to this string, it would be flying off straight ahead. However, the centripetal force provided by the string causes centripetal acceleration, which changes the direction of the velocity. So instead of it going straight, it becomes circular. The airplane's velocity continues to change, causing it to travel in a circle. The center of the circle is defined by the direction of the centripetal force. So the direction is the end of this string. If the string is cut, the centripetal force would vanish and the plane would travel straight in the direction of this blue arrow. So this is a drawing that's very similar to what we did in our experiment. In the experiment, we found that it took less time for the washer to make 20 circles when there were 4 washers hanging on the end of the string rather than 2 washers. So the indication is that the washer traveled faster when there was more weight on the string. More weight equates to more centripetal force. So the larger the centripetal force, the faster an object can travel in a circle of a given size. At the end of the experiment, we discovered that the circle with the lone washer was traveling, became smaller with 4 washers than 2 washers. So as we added weight on the end, this circle decreased. The indication then is that the larger the centripetal force, the smaller this circle will be. So in summation about this experiment and centripetal force, circular motion requires centripetal force. The larger the centripetal force, the faster an object travels in a circle of a given size. At a given speed, the larger the centripetal force, the smaller the circle. So that's what you should have in your notes there. If you need any assistance with this, be sure to contact me, and we'll be moving on to the next video.